Welcome to my little corner of the internet, where we celebrate creativity and growth. Thank you for joining us today as we dive into Radon's theorem. In geometry, Radon's theorem on convex sets, published by Johann Radon in 1921, states that any set of D2 points inward can be partitioned into two sets whose convex hulls intersect. A point in the intersection of these convex hulls is called a Radon point of the set. For example, in the case D2, any set of 4 points in the Euclidean plane can be partitioned in one of two ways. It may form a triple and a singleton, where the convex hull of the triple triangle contains the singleton. Alternatively, it may form two pairs of points that form the endpoints of two intersecting line segments. Moving on to the next segment, we have proof and construction. Consider any set x d rid of D2 points in D-dimensional space. Then there exists a set of multipliers a D2, not all of which are zero, solving the system of linear equations. Some I x I quad some I because there are D2 unknowns, the multipliers, but only D1 equations that they must satisfy one for each coordinate of the points, together with a final equation requiring the sum of the multipliers to be zero. Fix some particular non-zero solution a D2. Let Ix be the set of points with positive multipliers, and let Jxi be the set of points with multipliers that are negative or zero. Then I and j form the required partition of the points into two subsets with intersecting convex hulls. The convex hulls of I and j must intersect because they both contain the point. Sum xi in ifraka ia xi sum xginja fraka gia j where a xi ia I xj your j. The left-hand side of the formula for P expresses this point as a convex combination of the points in I, and the right-hand side expresses it as a convex combination of the points in J. Therefore, P belongs to both convex hulls, completing the proof. This proof method allows for the efficient construction of a Radon point in an amount of time that is polynomial in the dimension, by using Gaussian elimination or other efficient algorithms to solve the system of equations for the multipliers. Now, let's delve into the intricacies of topological Radon theorem and explore its various aspects. An equivalent formulation of Radon's theorem is: if there's any affine function from a D1-dimensional simplex Erd toward, then there are two disjoint faces of Erd whose images under intersect. They are equivalent because any affine function on a simplex is uniquely determined by the images of its vertices. Formally, let be an affine function from Erd toward. Let vd2 be the vertices of Erd, and let xd2 be their images under. Either original formulation, the xd2 can be partitioned into two disjoint subsets, e.g. xii in I and xjj in j, with overlapping convex hull. Because f is affine, the convex hull of xii in I is the image of the face spanned by the vertices vii in I, and similarly the convex hull of xj in j is the image of the face spanned by the vertices vj in j. These two faces are disjoint, and their images under f intersect as claimed by the new formulation. The topological Radon theorem generalizes this formulation. It allows f to be any continuous function, not necessarily affine. If there's any continuous function from a D1-dimensional simplex Erd toward, then there are two disjoint faces of Erd whose images under intersect. More generally, if Kelvin is any D1-dimensional compact convex set, and is any continuous function from Kelvin to D-dimensional space, then there exists a linear function g such that some point where g achieves its maximum value and some other point where g achieves its minimum value are mapped by to the same point. In the case where Kelvin is a simplex, the two simplex faces formed by the maximum and minimum points of G must then be two disjoint faces whose images have a non-empty intersection. The same general statement, when applied to a hypersphere instead of a simplex, gives the Bus-Coulomb theorem, that must map two opposite points of the sphere to the same point. With our curiosity piqued, let's embark on a dedicated exploration of proofs and its fascinating intricacies. The topological Radon theorem was originally proved by Erwin Bojci and Imre Bernyi in the following way: construct a continuous map G from the d-dimensional sphere to Erd1, such that for every point x on the sphere, x and gx are on two disjoint faces of Erd1. Apply the Basiculum theorem to the function fg, which is a continuous function from S to Erd. The theorem says that, for any such function, there exists some point y on st such that f y. The points g and gy are on two disjoint faces of Erd1, and they are mapped by f to the same point of Erd. This implies that the images of these two disjoint faces intersect. Another proof was given by Lslovsh and Alexander Schruchfer. A third proof was given by Geometrik let Kelvin be the simplex Erd1, and let K2 be the deleted join of Kelvin with itself. The geometric realization of K2 is homomorphic to the sphere St1, therefore, the index of K2 equals D1. The topological Radon theorem follows from the following more general theorem. For any simplicial complex K, if the index of K2 is larger than D, then for every continuous mapping from K to Erd, the images of two disjoint faces of Kelvin intersect. Let's now zoom in on applications and uncover the hidden gems that lie within. The Radon point of any 4 points in the plane is their geometric median, the point that minimizes the sum of distances to the other points. Radon's theorem forms a key step of a standard proof of Helly's theorem on intersections of convex sets. This proof was the motivation for Radon's original discovery of Radon's theorem. Radon's theorem can also be used to calculate the VC dimension of d-dimensional points with respect to linear separations. There exist sets of D1 points, for instance, the points of a regular simplex, such that every two known empty subsets can be separated from each other by a hyperplane. However, no matter which set of D2 points is given, the two subsets of a Radon partition cannot be linearly separated. Therefore, the VC dimension of this system is exactly D1. A randomized algorithm that repeatedly replaces sets of D2 points by their Radon point can be used to compute an approximation to a center point of any point set in an amount of time that is polynomial in both the number of points and the dimension. As we progress, let's shine a spotlight on related concepts and examine its intricate interplay within our topic. Geometric median. The Radon point of 3 points in a one-dimensional space is just their median. The geometric median of a set of points is the point minimizing the sum of distances to the points in the set. It generalizes the one-dimensional median and has been studied both from the point of view of facility location and robust statistics. For sets of 4 points in the plane, the geometric median coincides with the Radon point. Tverbud's theorem. A generalization for partition into R sets was given by and is now known as Tverbud's theorem. It states that for any set of D plus a 1 plus a points in Euclidean D space, there is a partition into R subsets whose convex hulls intersect in at least one common point. Carfodori's theorem states that any point in the convex hull of some set of points is also within the convex hull of a subset of at most D1 of the points, that is, that the given point is part of a Radon partition in which it is a singleton. One proof of Carfodori's theorem uses a technique of examining solutions to systems of linear equations, similar to the proof of Radon's theorem, to eliminate one point at a time until at most D1 remain. Convex geometries. Concepts related to Radon's theorem have also been considered for convex geometries, families of finite sets with the properties that the intersection of any two sets in the family remains in the family, and that the empty set and the union of all the sets belongs to the family. In this more general context, the convex hull of a set south is the intersection of the family members that contain S, and the Radon number of a space is the smallest R such that any R points have two subsets whose convex hulls intersect. Similarly, one can define the Helly number H and the Carfodori number C by analogy to their definitions for convex sets in Euclidean spaces, and it can be shown that these numbers satisfy the inequalities H1. Radon theorem for graphs. In an arbitrary undirected graph, one may define a convex set to be a set of vertices that includes every induced path connecting a pair of vertices in the set. With this definition, every set of 1 vertices in the graph can be partitioned into 2 subsets whose convex hulls intersect, and 1 is the minimum number for which this is possible, where is the teak number of the given graph. For related results involving shortest paths instead of induced paths, see and. Don't forget to check out my other videos for more valuable content.